All right, let's get right into it. So, you're constantly hearing about AI models getting bigger and bigger, right? We're talking billions, even trillions of parameters. But have you ever stopped to think, how on earth do you build something that massive without it costing a fortune, like the energy budget of a small country, just to run it? Well, that's exactly what we're going to unpack today. We're looking at the incredibly clever architecture that makes it all possible, the mixture of experts. I mean, this is the question, isn't it? It's the big challenge the whole AI world is facing right now. We all want these models to have this vast, almost encyclopedic knowledge, but at the same time, they've got to be fast and efficient enough for us to actually use them. So, how do you get the best of both worlds? Turns out, the answer isn't about making the model work harder, but making it work a whole lot smarter. And that really gets us to the heart of the matter, this fundamental issue in AI development. You know, for years, the recipe for smarter AI was pretty simple. Just make the model bigger. More data, more parameters, and you'd get better results. But that straightforward path, it's hitting a very real and very, very expensive wall. Yeah, think about it like this. Imagine having one single gigantic brain. Now, to answer any question, doesn't matter if it's what's the capital of France or some super complex physics problem, you have to light up the entire brain every single time. That's how traditional models, what we call dense models, work. It's kind of like using a supercomputer to run a simple calculator. It's powerful, for sure, but it's just incredibly inefficient for most things. Every calculation means activating billions of parameters, and that costs a ton of time and an absolute mountain of energy. So what's the fix? Well, instead of that one giant overworked brain, what if you had a whole team of specialists? And that, right there, is the beautiful, kind of elegant idea behind the mixture of experts, or MOE architecture. This comparison really just nails it. A dense model is like that one expensive generalist consultant who has to do absolutely everything. But an MOE model, that's like having a boardroom full of world-class specialists. So when a task comes in, say translating a sentence into Spanish, you don't need to bother the poetry expert or the calculus guru. Nope, you just call on the language specialist. And this is the key. The model as a whole can have this massive amount of collective knowledge, but you only pay the computational price for the specific expertise you need in that exact moment. So here's the most crucial takeaway. The MOE architecture lets a model have a huge number of parameters, but only a tiny fraction of them, these experts, are actually fired up for any given input. It's all about conditional computation. You get the knowledge of a massive model, but with the speed and the cost of a much, much smaller one. Okay, so that all sounds great in theory, right? But how does it actually work under the hood? Well, the real magic is in how the system knows exactly which expert to call for any given job. It's really like a little four-step dance. First, a piece of data, we call it a token, arrives. Next, a component called the router or the gating network takes a look at that token. Just think of it like a brilliant receptionist. It instantly knows, for this task, I need this specialist or maybe these two specialists. It sends the token over to them. Those experts then get to work at the same time, in parallel. And finally, their individual results are intelligently blended together to create the final output. So let's just quickly break down those key parts. You've got the router, that's the decision maker. The experts themselves are usually pretty simple, specialized neural networks that do all the heavy lifting. Then there's this thing called the capacity factor, which is basically a rule that says how many tasks any one expert can juggle at a time. And finally, you have load balancing. Think of it like a traffic cop. It's a clever bit of code that makes sure the work is spread around evenly, so you don't have one expert getting totally swamped with requests while the others are just sitting around doing nothing. Okay, now let's talk about the results, because this isn't just some cool theoretical idea. The performance gains out in the real world are, well, they're staggering. This is where Mo really goes from being a neat concept to a genuine breakthrough technology. 7 times faster. Seriously, that's not a small improvement. That's a fundamental shift in how things are done. Google's Switch Transformer, which was a huge landmark MOE model, saw up to a 7-fold speed up in pre-training. In the AI world, where training a big model can take weeks, even months, that kind of acceleration is an absolute game changer. And the innovation just keeps coming. It's not only about the architecture itself, but also the code that runs it. Optimized systems like Megablocks are squeezing out even more performance, getting up to a 40% speed up over previous MOE methods. The whole ecosystem is just evolving at a breakneck pace. And you can really see that acceleration right here. The modern concept kicks off around 2017. 4 years later, by 2021, we have trillion parameter models like Switch Transformer and GLAM that prove this thing works at an insane scale. And then, just a couple years after that, in 2023, models like Mixtral 8x7b bring this incredibly powerful tech to the open source community, which, believe me, is a huge, huge deal. Okay, so we know the router, our smart receptionist, is picking the experts. But that brings up another really interesting question. For each task, how many experts should it actually pick? Yeah, does it send the job to just the single best specialist it can find? Or is it actually better to get a second opinion? This choice creates a really fascinating trade-off between pure speed and overall quality. And this gets us into a cool design choice. On one side, you've got what's called top-one routing, which models like Switch Transformer use. It's simple, one token goes to one expert. It's the fastest, most direct route, less communication overhead. But on the other side, you've got top-two routing, which is famously used by Mixtral. Here, every token gets sent to two experts. Now, this takes a little more computation, a little more communication, but combining the outputs from two specialists often gives you higher quality, more robust answers. For a lot of folks, this top-two approach is really the sweet spot. So we've looked at the problem, the solution, the mechanics. What is the single most important thing you need to understand about Mixture of Experts? If you remember one thing, what should it be? This. This right here is the magic trick. With Mo, you can dramatically increase the number of parameters in your model, which is basically its total knowledge, without proportionally jacking up the amount of computation, or flops you need to actually run it. You get a brain the size of a library, but you only have to read 1 or 2 books at a time. You know, there's a quote from one of the sources that just says it all perfectly. You are essentially buying model quality, buying intelligence, by adding more and more parameters, more experts, but you're only paying the computational price for the few experts you actually use for each specific task. It's the ultimate have your cake and eat it too scenario for scaling up AI. And that leaves us with a pretty fascinating final thought. For years, computational cost has been this massive bottleneck, right? A huge hurdle on the path to more powerful AI. But now that this barrier is being so elegantly sidestepped, what new possibilities does this unlock? What happens when building a trillion parameter model is no longer some astronomical expense, but a practical reality? That is the exciting future that Mixture of Experts is helping to build right now.